Imagine standing on a wave-washed ledge of England's Jurassic coast as wind rattles the grasses and salt spray freckles your jacket. You glance down and see a three-toed impression, then another, then a braided ribbon of prints running along the stone like a lane through traffic. Broad circular craters mark the steps of long-necked herbivores. Narrow bird-like triangles signal the passing of carnivores. In early 2025, researchers reported Middle Jurassic trackways dated to about 156 million years ago. The announcement didn't just add another dot on a fossil map. It opened a window into motion, routine, and choice. Footprints, unlike bones, record moments while life is happening, a step placed. A push-off for traction, a pause while the ground firms. Some impressions here are so crisp they preserve claw tips and subtle skin textures, transforming a flat ledge into a living film still. For a channel like ours, dedicated to the stories behind the science, this site is more than news. It's a chance to walk behind the animals themselves, to watch how they used the same patch of earth, and to reconstruct a morning in deep time with the rigor of measurement and the immediacy of eyewitness detail. A footprint is physics translated into history. When a limb strikes wet sediment, it pushes grains aside, forces water upward, and creates a three-dimensional void bordered by a raised rim, the true track. Deeper strain deforms layers below, producing undertracks that echo the original, even if the surface is later scoured away. From these shapes, scientists extract numbers and behavior. Track length and width help estimate hip height, stride, and pace angle. Reveal gait was the animal walking, power walking, or running. Depth patterns show how weight rolled from heel to toe and which claw dug deepest for grip. Parallel lanes indicate coordinated travel. Tight juvenile prints beside larger ones suggest family groups. Toe splay records how feet adapted to slick ground. Sharp claw tips imply traction on a slope. Even the collapse of a rim can document a pause where weight lingered. We measure, compare, and model all of its speed from stride and hip height, mass from depth and sediment strength, posture from pressure distribution. The magic is that these inferences are testable. You can return with better scans, new experiments, and improved sediment data, and the prints will argue back with the same geometry. That's why tracks are powerful. They're observables, not guesses. During the Middle Jurassic, southern Britain sat near warm, shallow seas, low islands, lagoons, and broad tidal flats stretched across the region that would become Dorset. Twice each day, tides drew water off the flats, leaving slick mud and scattered pools threaded by ripple marks. Dinosaurs moved in to feed, to travel, and to cross between patches of higher ground. Each footfall compressed the waterlogged layers, creating crisp rims and subtle internal structures that later hardened. Fine silt drifted in to fill the impressions. Microbial mats stitched the surface shut like a seal. Over millions of years, additional sediments stacked above, their minerals cementing into limestone. Tectonics tilted some beds, waves planed others, storms ripped away weak layers while polishing resistant ones. Eventually, erosion trimmed the cliff back to reveal a clean, walkable surface at just the right height. That accident of geology matters. Trackways are fragile. Most are destroyed long before rock sees daylight. Here, preservation met exposure under conditions gentle enough to keep detail, yet bold enough to make the prints visible. When you look at the highway now, you see a collaboration across time dinosaurs, mud, microbes, sun, burial, uplift, and the sea, all signing their names on the same slab. Sauropod prints announce themselves with size before detail. Hindfoot impressions approach a meter across and show weak crescent claw traces. Smaller oval handprints sit slightly forward and inside, telegraphing a diagonal limb gait. In places, the trackway is narrow gauge, the feet hugging the midline. Elsewhere, it swings wide, hinting at anatomical differences among lineages that shared the flats. Strides fall in a steady rhythm, long enough to cover ground, short enough to keep momentum low on slick surfaces. Depth profiles often peak near the inner margin, consistent with columnar legs that loaded inward as the body shifted over the planted foot. A few steps carry faint ridge lines where skin or soft pads puckered against mud. Others bear micro slumps where waterlogged sediment oozed back after the foot lifted. Stand in one of these prints and the scale is immediate. The rim reaches your ankles, the floor cups your boots. You can trace how the next step would fall and feel the logic of a body distributing enormous mass with care. Herd movement becomes plausible, even obvious many big animals, all choosing the same firmer path, all accepting the slower pace that safety demands. The stone remembers every compromise. Theropod footprints look like giant bird signatures, 3 pointed toes, a narrow heel, and deep claw tips. Some are scarcely bigger than a man's hand. Others spread as wide as a dinner tray. A few tracks display pronounced toe splay, a response to slick ground that increases surface area and traction. Others show gouges at the tips where claws dug in as the foot pushed off. One sequence angles behind a sauropod lane, crosses it, then runs parallel several yards away as if shadowing at a cautionary distance. Another sequence lengthens, stride over several steps, a subtle acceleration, visible only when you measure center-to-center spacing and compare pace angles. Bones from this time and place are scarce for predators, but the tracks remove any doubt they were there, choosing the same corridor, exploiting the same firm ground, and timing their movements around the passage of heavier animals. Whether they hunted here or merely traveled efficiently is an open question, and a good one. The prints give us the data orientation, spacing, depth, and overlap. Behavior is the model we fit to those data. Sometimes the match is tight. Sometimes it's tentative. Either way, the corridor is a conversation between prey, predators, and mud. Behavior emerges when many measurements agree. At Dorset, multiple parallel sauropod lanes imply coordinated movement that goes beyond chance alignment. Juvenile-sized tracks hug adult paths at a consistent offset, suggesting close following and a protective envelope. Cross-cutting prints provide timing. In some places, theropod steps overlay sauropod impressions. In others, sauropod feet squash theropod rims, proving that traffic alternated. Areas with repeated churning and overlapping depressions appear where animals hesitated or milled, perhaps evaluating footing, perhaps waiting for water to drain. A few theropod prints show sudden, deeper toe tips and longer strides, a burst that reads like a jog between puddles. Sauropod pace lengths narrow briefly at a slope and widen again on the flat, an instinctive speed check you can graph from step to step. None of these patterns alone proves herding, parenting, or stalking. Together, they weigh the scales. Tracks shrink speculation to the size of evidence. You count, you map, you test against modern analogs, elephants on mud, emus on wet sand, and you keep only what survives comparison. The result is a storyboard, not names and species lists, but choices and constraints, the choreography of a morning written in pressure and clay. Dorset's highway belongs to a global map of dinosaur movement. In Texas, the Paluxy River has exposed intertwining sauropod and theropod tracks since the 930s. When floods scrub algae from limestone, the prints can look alarmingly fresh. Bolivia's Cal Orco Wall preserves thousands of tracks on a steep cliff, a former mudflat, tilted upright by tectonic buckling. Like a museum display, the earth built itself. China's Yunnan Basin holds track fields that document sauropods spreading across humid lowlands, while Australia's dinosaur stampede at Lark Quarry preserves a chaotic tangle interpreted as a sudden mass movement. Each site carries its own biases, sediment strength, exposure style, and later deformation, but Together, they let scientists compare speeds, gaits, and community structure across continents and ages. That is the promise of ichnology at scale-independent surfaces, measured consistently. Building a data set big enough to test ideas about migration corridors, predator diversity, and environmental preference. Dorset adds a rare Middle Jurassic data point to a record otherwise dominated by late Jurassic and Cretaceous sites. Its value is not only in its beauty, it is in its timing. It catches sauropods early in their rise and theropods diversifying into the swift, elegant hunters that would later rule the Mesozoic stage. Modern ichnology blends fieldcraft with high-tech tools. Teams fly drones on pre-planned grids to generate orthophotos, then build three-dimensional meshes via photogrammetry so every footprint can be measured without being touched. Handheld laser scanners capture micro-relief fine ridges, skin puckers, and claw drags that traditional casts might miss. Depth-encoded maps let researchers compare prints objectively, stripping away shadows. Silicone peels and plaster casts still matter. They create durable archives that can be studied when storms have done their worst. In the lab, experimental ichnologists press weighted molds into muds of known strength, then dry, flood, and shear them to replicate real surfaces. Comparing those test prints to field scans constrains speed, mass, and foot posture. Even statistics have footprints. Orientation histograms test for preferred travel direction. Variance in stride length measures terrain difficulty. Clustering algorithms flag lanes likely made by the same animal. None of the tools replaces a careful eye. Field notes still record the telltale's collapsed rims, perched edges, tiny handprints beside big tracks that scanners can miss. The strength of the science is the braid observation, experiment, and computation twisting together until behavior emerges with clarity. Skeletons tell us what kinds of animals could exist. Trackways tell us what kinds of days they actually lived. Bone beds bias toward dramatic endings, drought die-offs. River traps, lucky burials. Tracks bias toward routine, the morning commute, the detour to a firmer patch, the pause at a puddle edge. They raise the visibility of animals that rarely preserve as skeletons, especially medium-sized forms whose bones were scattered or never buried. They reveal interactions bones struggle to prove: parallel travel, following, avoidance, loitering. They help date behaviors. A surface bristling with prints is a snapshot, not a smear through time. For public audiences, footprints carry an emotional charge bones rarely match. You can stand in a track, you can feel the rim against your boot, and imagine your weight as theirs. Museums know this. Track slabs on the floor are magnets because they are invitations. Try the stride, measure your foot, walk beside a ghost. Science rides that emotion toward careful measurement, and careful measurement returns the favor by deepening wonder. The loop is healthy. It turns awe into data, and data into awe again. A feedback that keeps both curiosity and discipline alive. Follow the line of prints to the present, and you find a rope line, a research team, and a gray sea beyond. The work looks modest: tapes, notebooks, drone batteries, kneeling pads. Yet, the results are large. A pace angle is an argument. A parallel lane is a claim about social life. A deep claw tip is evidence of traction and posture. Layer those measurements together, and you reconstruct a morning 156 million years ago, herds walking, youngsters keeping close, predators choosing the same firm path across the flats because physics gave everyone the same answer. In that reconstruction, the dinosaurs lose none of their grandeur. If anything, they gain reality. They slow down, they slip, they hesitate at slopes and speed up on the hard. They cease being movie monsters and become animals, heavy and purposeful, solving the same problems we do when a trail turns to muck after rain. A final thought for anyone visiting a track site: slow down. Stand where the prints are densest and breathe. Look for the small details, first the toe drags, the collapsed rims, the faint handprints beside the big hind feet, and let the picture grow outward. Imagine the ground.